Hello, everyone. These next few lectures, we're going to start diving into our first algorithm. Today, we'll mostly cover some preliminaries and not actually get into the algorithm, but over the next, including today, about 4 lectures, we'll start getting into it. There are many optimization algorithms out there, and we'll discuss quite a few over the course of the semester. But we're going to start with some unconstrained optimization. This is a very fundamental gradient-based methods that, even for methods that don't use gradients, use a lot of these ideas. So we're going to start with these fundamentals. Give me a second here, and I'm going to share my screen. Okay, these methods are all under this category of unconstrained optimization, and this particular method is a line search-based method, and we'll see what that means shortly. Maybe next time. Okay, and just to remind you, what we're trying to solve right now is not the full optimization problem that we originally started with, but an unconstrained one. So we want to minimize some objective, and remember that's quite general. That can include maximization as well. And we're going to vary some design variables. There are no constraints on this problem, just an unconstrained regular problem. Okay, and we are going to use what are called gradients. This is a form of gradient-based optimization. So first we need to discuss what is a gradient. So you may remember back from multivariable calculus, for some of you it may have been a while, but you're all very familiar with the concept of a derivative, and a gradient is just a derivative in a multi-dimensional space. Okay, so define it this way. This is the gradient of some function f. It's a vector, so I'm going to write this as a column vector. So instead of just being a scalar like a gradient in one dimension, it will have multiple components for each dimension. So it'll be partial derivative of f with respect to x1. That's the first entry, the partial of f with respect to x2, and so on up to the partial with respect to xn, depending on the dimensionality of the space. If you've forgotten partial derivatives, I'd encourage you to go back into the appendix and do some of the review. But in brief, right, a partial derivative means that all the other variables we hold constant and only vary that one. So this is the definition of a gradient. It basically generalizes that one-dimensional derivative and tells us how our function changes in every coordinate direction. If you wanted to write it based on ideas from calculus, we could say that ith derivative, remember, it comes from a limit where a step size goes to 0, and f is really a function of many things, x1 to xi, and this xi, since we're taking the ith derivative, let's just be really specific here and just do one. Let's say x2. Let's say there's 3 variables, right? Let's say I have f and it has 3 variables, x1, x2, x3. We would take the x2 one and add epsilon to it. For example, this is just a definition using the calculus theorem, and then we would divide by epsilon. Okay, and the limit as that goes to 0. So we're taking a small step in that coordinate direction, dividing by that step size, and that is the definition of derivative as that goes to 0. Well, let's look at what this means, maybe give an intuitive explanation. This vector, remember this gradient is a vector, it's a vector that will point in the direction of greatest function increase. So the gradient is a different vector at every possible point. So if I'm at this point, I'm going to get a different gradient vector than at this point. So here at this point, it's going to point in the direction of function increase. So this is, say, a minimum here. This is like a bowl. So it's going to point away. It points in the direction in which the function is increasing the fastest. Okay, so here's another example of this, maybe clearer to show more contours. So here's a bunch of gradient vectors evaluated at many points on this function. So this function has a minimum over here and a maximum over here. You can see that these gradient vectors are going to point up the slope, right, towards the direction of steepest increase. Physically, that's what a gradient vector is going to mean. Okay. Now we also want to review the concept of a directional derivative. Now, remember, the gradient gave me the derivative in these coordinate directions, right? X1, X2, X3, and so on. Now that's somewhat arbitrary, right? Because that depends on how I define my coordinate system. A directional derivative says I want to know the rate of change in a particular direction, right? And we'll call that direction P. So the syntax we'll use is it's the derivative, the directional derivative of some function f in the direction P. We could define it the same way, going back to the calculus theorem. It's going to be a limit as the step size goes to 0. We'll take f of x. Remember, x is a vector. We add some small step in the direction of p. We subtract off f of x, and we divide by epsilon. Okay, that's just a definition from using a calculus type of idea. But in practice, right, this is how this will be used. We can get, if we know the gradient, then we just take the dot product of that gradient with this vector p. And that's going to give us the rate of change of the function in the direction of p. That's very useful, right? Because we may want derivatives in other directions besides our coordinate directions. Okay, and again, if you're not familiar with this syntax, I'd encourage you to review the section on linear algebra in the appendix. This is just a dot product, if you remember. So these are both vectors. So you could think of it as a row vector and a column vector. And if I multiply those two together, it's a dot product. But let's look at some pictures to maybe try to make this a little clearer. Here's an example. Looks like the function didn't quite transfer over. This is actually a three-dimensional function. Probably didn't get rendered correctly in the PDF, but you can see in the book. But really, this is the key idea here. Here are the contours of that function projected onto it. The gradient points in some direction of steepest increase, right? And now we're saying we want the derivative, the directional derivative in this direction p, right? This is some direction that we chose. So one way to think about that dot product, right? It's the projection of that gradient. So I take this right angle here. It's the projection of the gradient into that direction. Okay, so, or in other words, it's the component of the gradient in the direction p. And so again, if we write the definition, the directional derivative of f is going to be the gradient. It's the dot product of the gradient in that direction. Or if you remember, what's the definition of the dot product? Well, it's the magnitude of each of these vectors times the cosine of the angle between them. That's just the definition of a dot product, right? Or another way to express it. So from this definition, how do we know then that the gradient is the direction of steepest increase? Take a moment and look at that equation and see if that will make sense to you. So remember that the dot product, where is this going to be maximum? When is the dot product maximum? It's the maximum when theta is 0, right? That's the biggest dot product. And so when theta is 0, that means p is pointing in the direction of the gradient. So the biggest change, that means the biggest derivative, the biggest rate of change is going to be in the direction of the gradient of f. Right? We can see that just from this definition here. So any other direction is not going to be as steep. To take that further, we can maybe look at directions all the way around, right? If we're thinking of this as a compass, all the possible directions. Okay, again, gradient of f, that's the steepest increase. And here's p, and I can choose p to be all sorts of directions. It can point anywhere around this 360 degrees, or in general, this is 2D, right, 360 degrees, but in general, in any direction in some n-dimensional space. Everywhere on this side, right, where this theta angle is less than 90 degrees, that dot product is going to be positive. So these will all give me positive directional derivatives. On the other hand, if I choose directions this way, these will all be negative directional derivatives. And in fact, this one that's exactly opposite to the gradient f, that'll be my steepest decrease. That'll become important later. So this is my steepest increase. This is my steepest decrease. And of course, if I pick a line that's perpendicular, the dot product is 0, then for small changes, right, my dot product will be 0, I should say, for directions that are going to be orthogonal to my gradient. Okay, so that's just to give you some feel for what a directional derivative means. Again, this is the biggest increase, this is the biggest decrease. I can get less increase or less decrease in different directions, but these are all going to give me positive values. These are all going to give me negative values. This is going to come into play later because as we work on these minimizations, we're going to want to go into directions to where the function is decreasing. That's going to be this blue area here. So we're going to be free to choose directions over here that lead to decreases in my function value. All right, and then another sort of review concept is what's called the Hessian. So the gradient was this generalization of the derivative. The Hessian is going to be this generalization of the second derivative. So in index notation, we could write it this way. It's the partial of f with respect to xi and xj, right? It's a second derivative. We'll also write it this way. This is the second derivative of f of x, and often we give it a special notation h for a Hessian. And we could also write this in matrix form. So for example, this first entry would be, whoops, the second derivative of f with respect to x1 twice. This would be the second derivative of f with respect to x1, xn, second derivative of f with respect to xn, x1, and then the second derivative of f with respect to xn twice, right? So basically every combination of the derivatives based on the dimensionality. So as you can see, this is going to be a square matrix. If I only had 2 dimensions, this would just be a 2 by 2 matrix, 3 dimensions, 3 by 3. And you may remember the order of derivatives doesn't matter. This is just from calculus, right? So this has to be a symmetric matrix, right? Because the derivative with respect to xi, xj has got to be equal to the derivative with respect to xj, xi. And you may remember I can exchange the order of those derivatives without changing anything. So those will be equal, which means that this is a square and symmetric matrix. Okay, so with those together, we can, we talked last time about Taylor series, but we can now use our new notation to maybe express this in a different way than we did last time. So imagine I've got some function. This is something that we're gonna see several times over the next week or two. We're gonna be at some point x, and I wanna consider some step nearby. P is gonna be some step. It's like that direction that we just talked about, okay? So that's some direction vector that I wanna evaluate at. So for some small step P, I can do a Taylor series. That's gonna be equal to f of x plus, now I've got the first derivative term, that's the gradient of f, dotted into P, the dot product of that with P, or I could write f of x, plus now I've got my second derivative term, so I've got the 1/2, and this is how we write this in matrix notation. Again, you may want to review linear algebra plus higher order terms. So again, this is a second order term, this is a matrix, this is a vector, this is a column vector, this is a row vector since it's transposed. So when I've got a row vector, a matrix, and a column vector, this whole thing gives me a scalar, right? So all of these are scalars. There's a scalar, dot product gives me a scalar, this is a scalar, and I could have higher order terms. So what this will look like, here we've taken a Taylor series about this minimum. The blue is the original function, and notice it's, you know, not some nonlinear function. And here we just took a second order Taylor series, so it's going to give a quadratic. And so these black lines are contours of that quadratic function. Notice that it gives a pretty good approximation when I'm near the minimum or near the point where I took the Taylor series about. Because again, remember, a Taylor series is going to be accurate the closer I get to where I am. The further I get away, I have no guarantees, right? So you can see as I get further away, it's a less good approximation of the actual function. You can see these contours differ quite a bit from the blue lines. But as I come closer back to the point at which I was evaluating, in other words, small step sizes, this should be a pretty good approximation of my function. Again, remember, these are contour lines, so you could think of this as like a bowl, right? Imagine these are rings of constant elevation. So there's a constant elevation, another elevation that's a bit higher. So this is kind of has this bowl shape where it's not quite circular bowl. It's kind of this elongated bowl. That's what a quadratic, right? Like this parabola would look like in this 2 dimensions. Okay, so that's Taylor series. Now we have the pieces together to answer maybe the first question we need to deal with when we're trying to find an optimum, which is, how do we know that we're at an optimum? What does it mean for a point to be optimal? Okay, so I'm going to go through a bit of a derivation that may feel a little bit convoluted, but hopefully it'll sink in. And when we connect it to 1D, I think you'll recognize it, or at least the result. So let's do the exact same thing we just did. Let's do a Taylor series, but let's do a Taylor series assuming we're at the optimum. Let's assume that we solve this. Okay, let's say we're at the optimum, so X star, that's our notation for optimum, right, is a star. And so I want to take a Taylor series about that point. So as we just saw, we're going to get our first order term, evaluated X star, plus a first derivative term, gradient, right, evaluated X star. We take the dot product with P, and then we get our second order term. That's going to be the second derivative, or the Hessian, right, H of X star times P. And we're just going to stop at second order term, right, but there could be higher order terms. Now, what would it mean if this was truly a minimum? Okay, so what would it mean? So X star is a minimum. So we could ask the question, how then would this function value compare to this function value? So this is at the minimum, and these are at points that are near the minimum, right, where we've taken steps in any arbitrary direction. P, we haven't said what P is, it's any possible direction, okay? How do I know I'm at the minimum? What must be true if I compared this function to this function? Well, if this is truly a minimum, then everything nearby has to be bigger, right? Because I'm at the minimum, so no matter which direction I go, the function had to increase. So in other words, if this truly was a minimum, then we could say that f of x plus p has to be greater than or equal to f of x star, right? This is a minimum, so everything around it has got to be bigger for all p, right? This is a symbol for all. Oops, well, I'll just write it out for you. It's an A, upside down A, for all p, for any p, okay? Any direction I choose, this had better be true. That's what it means to be a minimum. Okay, so let's say that that's the case. That would also mean that, for example, f of x star plus p minus, let's just move everything to the other side, is greater than or equal to 0, right? I just move things over. So we could do the same thing here. I'm going to move this over, okay? Then if I move this over, then that's equal to this, and that's then equal to this side. So I'm saying this whole thing here now has to be greater than or equal to 0. So I didn't write all that out, so I'm just going to do it again. Let's move this over. That's the same as this, right? So we're saying that has to be greater than or equal to 0. So that means this thing here, which is equal to this side, has to be greater than or equal to 0. So in other words, what we're saying is that this term that's left, gradient of f plus 1/2 p h of x star p, that must be greater than or equal to 0, okay? Just following from what we said above. Okay, well, if that's the case, let's assume that p is small. We can choose p to be anything. If I choose a small enough p, then this term is always going to be much bigger than this term, right? Because this is a first order term, this is a second order term. So in other words, since I need this to be true all the time, I need it to be true even for very small p. So it must be that this first term has to be greater than or equal to 0. But remember, this has to be true for any p, okay? So let's go back, look at this figure, for example. Here's the gradient. I'm at my optimal point. It's going to have some gradient for whatever direction it happens to be. I need the gradient dotted into p to be positive for any p. But that clearly can't be true, right? Because I'm free to choose any p, so I could choose a p over here. I could choose a p over here that's going to be negative, right? So that dot product is negative. And I just said I need that dot product to be positive, greater than or equal to 0 for this to be a minimum. So that means that if this is a minimum, the only way that this can be true is if that gradient is 0. If the gradient is 0, then for any p I choose, this will be satisfied. There's no other way, right? Because if the gradient is anything that's non-zero, I can always choose a p that will make this term unsatisfied. And if that's the case, then there's some direction I could go that's still downward and I'm not at a minimum, right? So to say it again, if the gradient is non-zero, there's some direction I could go that's downwards. So I'm not at a minimum. So the way I know I'm at a minimum, or really an extreme point, is that the gradient of f is 0. Now what does that mean again? Remember, the gradient is a vector, so that means every entry in that gradient is 0, right? That's a vector of just all zeros. Now, this shouldn't be too surprising if you think back to calculus, right? Remember, just in 1D, if I had some function and I wanted to find the minimum, how do we know if they're minimum? Right, we said the derivative, that's a horrible line. It's at the point, I can't draw it. It's at the point where the derivative equals 0, right? This is that exact same idea, only in n dimensions. The gradient is going to be 0. The first derivative, the derivative in all directions is 0. Okay, so this analogy here probably motivates the next point, which is we actually don't know that this is a minimum. It could be a maximum, right? It could actually be a saddle point. We don't know with just the first derivative. We know it's an extremum, so that's kind of the first condition. We also need to look at the second condition. And that goes back to this equation here. We just said the gradient is 0 to minimum, so this term is gone. So now we are left with this term here. For it to be a minimum, we need this criteria to be satisfied. Physically, what this means is that the curvature must be positive. You remember curvature, right? A positive curvature in so this one-dimensional function is up like this, right? Smiley face positive, whereas a negative curvature would be a downward function like this, right? So this says that the curvature has to be positive in any direction that I choose, right? So now we're in this multi-dimensional space, so I don't have just one direction to do in 1D. I can look in any direction I go, it's got to be positive, right? So it looks something like this in just 2 dimensions, that if I'm at a minimum, every direction has positive curvature. You may also remember from linear algebra, this form means that H is positive semi-definite. The stronger form is that it's positive definite. We won't worry too much about the distinction here, but essentially, this is the intuition here, that the curvature is positive in every direction. Well, first we have to say the gradient is 0, we're at an extremum, and if the curvature is positive in every direction, then that extremum is a minimum, okay? So just to recap here, what we've derived is that the criteria to define a minimum. This is how we know our algorithm is done. We haven't talked about how this algorithm works, but we at least know how to, or when to stop. And when do we stop? We stop when, the derivative gradient is 0 and the Hessian is positive definite. Okay. Now in calculus, sometimes you actually just solve for this, right? You had little simple problems with analytic expressions that you could solve. We can't do this in general engineering problems where we've got some, code. We can't analytically find a place where this is 0. So we're going to have to use these iterative methods. Also in practice, as we talked about in the last lecture about numerical methods, we're never actually going to get to 0, right? We have some machine precision here. We have some finite precision that we can represent things with. So we're going to use some sort of tolerance. So we're going to look at the magnitude of the gradient, and we are going to terminate when that magnitude is less than or equal to some tolerance, tau. So we choose some tolerance. Tau is typically around 1 to the minus 6, and often it's a relative tolerance. We'll discuss that a bit more later. But the point here is that we'll never get to exactly 0, right? Because we have some finite precision. So we'll just choose some tolerance that says the gradient is within finite precision, some small number. You may want to review in the appendix about norms. It may not be a review, may also be new, but to you, but it's something that comes, should be a review from a linear algebra. You'd be quite familiar with what's called a two norm. This is where we take each entry, we square it, sum them together and square root it. It's also Euclidean distance. It's what we're used to thinking about, what's the distance between points, but generalized in any dimension. You can use many different types of norms. And like I said, that one's called a two norm. Perhaps a common one is what's called the infinity norm. You could think of it the same idea, like it would be taking each entry, square it, add them, and then square root them. But instead you take each entry, take it to the infinitieth power, add them together, and then do the infinitieth square root. It has the effect that it's going to take whatever value is biggest, and it's going to become so much larger than any others that they're negligible. So in other words, what this does is it just takes the maximum value. And I should say maximum magnitude. So it would be, if you took the absolute value of every entry, whether it's positive or negative, doesn't matter, just took it the magnitude, it's going to take the biggest entry. So in other words, we're taking every entry in the gradient and forcing it to be below this tolerance, rather than like some sum of the squares or whatever. So this is a very common criteria here. The other thing to mention here is that we will generally not explicitly check this. As we'll see in the algorithm, we will always use a descent direction. We'll always go down. Every time we can guarantee that our direction is going to go down, and we are going to take steps that are going down. So if we're always going down and we hit one of these points, then we know we're not going to a maximum, we're going to get to a local minimum. So in practice, we don't actually have to check this. We just have to check this one, that our gradient, the entries in our gradient have fallen below some tolerance, or the magnitude of those entries. Okay, so again, we haven't talked at all about how this algorithm will work, but we have defined how we know we're done. We've reached a minimum. Okay, so again, to recap here, this is the problem we're trying to solve. And what I would, if you didn't do this in class, or if you're just watching these instead of being in class, I would encourage you to think about this before next time. Think about how you would construct an algorithm. So we just talked about how to quit, how to know when you're done. Think about how you would construct an algorithm. And I would think about it this way. Imagine that evaluating F is expensive. So you can't just choose lots and lots of X's and just say, let's just randomly sample tons and tons of points and pick the best one, okay? In engineering, most of the time, our analysis is gonna become computation expensive. So we wanna be careful. We want to efficiently find the minimum. And remember, like we gave this analogy of searching a mountain, but it's kind of like a mountain with a very deep fog where you know nothing. And it's not a mountain where you walk around, so maybe a mountain's not a good analogy. It's a mountain where you say, for example, choose a latitude and longitude pair, and I tell you this is the elevation at that point. And you say, okay, here's a new point I want to check, and I tell you the elevation. So you're kind of just, you can jump around wherever. So with those parameters, which is basically how it's going to work, right? You're going to tell an optimizer, or an algorithm is going to say, evaluate here. Function is going to return back and say, here's my objective. And you're going to say, okay, here's a new point I want you to look. And then it's going to give you an objective. And now we know how to quit, but the question is, how do we choose which points we want the analysis to evaluate? In other words, what's the algorithm? So something to think about before next time. Construct a method in your mind, or write it down. There are, of course, tons of algorithms. There's no right answer here. This is really just to get you thinking about maybe some of the challenges involved in doing this before we talk about it in the next lecture. So we'll see you next time, and we'll get into some of those details about how this will work.